Welcome to this week's first lecture. In the last lecture, we have seen how to find the Jordan canonical form, and we have seen the concept of a chain or a Jordan chain, which we use in the formation of the P matrix that would bring the matrix A into its Jordan canonical form. So I will first make the usual introduction here. So we know that when we have an A matrix, A in C n by n, its characteristic polynomial is going to be in this form. So I from 1 to k, s minus lambda I to the power ri. And the minimal polynomial will have the same form, I from 1 to k, s minus lambda I to the power mi. Okay? And we know that summation of the ri's is equal to n, I from 1 to k, and furthermore these mi's are between 1 and ri. So remember, we have defined this matrix sigma I, which is important for us. So that is A minus lambda I identity. That is the definition of the matrix sigma I. And we use this matrix in writing these matrices in writing the decomposition of Cn into a direct sum decomposition into these null spaces. Sigma 1 m1, sigma 2 m2, going until sigma k mk. All right? And we know that the dimensions of each of these spaces are R1, R2, and going until Rk. All right? And then we looked at, in order to be able to find the Jordan canonical form, we looked at the structure of these null spaces, which are invariant under A, because they are null space of a polynomial of A. And we know that the smallest null space is the eigenspace, null space of sigma I. It is the eigenspace belonging to the eigenvalue, ith eigenvalue lambda I. And we have null space of sigma I square going until null space of sigma I mi minus 1 and null space of sigma I to the power mi. We know that this is the largest null space possible with the powers of the matrix sigma I, and the dimension of this one is Ri, as we have seen. So by looking at the dimensions of these null spaces, which we can actually form the Jordan canonical form of the matrix A. So if we know only these dimensions without knowing the matrix A, we can extract what the Jordan canonical form would be. And here, what was the main fact that we used in forming the Jordan canonical form? It was these consecutive dimension differences. Dimension of null space of sigma I is the eigenspace dimension. It's the number of eigenvectors belonging to the eigenvalue, linearly independent eigenvectors belonging to the eigenvalue lambda I. And the other spaces are generalized eigenspaces. Okay? And we know that these dimension differences, consecutive dimension differences, gives us the size and the number of Jordan blocks. So here, what we have learned is that dimension of null space of sigma I to the L minus dimension null space of sigma I to the L minus 1 is the number of Jordan blocks with size larger than or equal to L for lambda I. Okay? And this is the main fact that we use in extracting the Jordan canonical form for a matrix. All right? And we also know that this mi is the size of the largest Jordan block for lambda I. All right? So these were the facts that we have extracted while we try to obtain the Jordan canonical form. And now we actually passed in the last lecture to the topic of how to form the matrix P, which would put the matrix A into this Jordan canonical form. So we are asking the following question. If the Jordan canonical form is given as P inverse AP, what is P? Okay? We know what J is based on these facts, these null space dimensions. Then we are concentrating on how to find such a P matrix which would satisfy this equation. This is a basis change operation. So when or which basis set for Cn gives us the Jordan canonical form as our simple block diagonal representation. Okay, and the answer is really straightforward here. We have to find basis sets for each of these invariant subspaces to form the simple block diagonal representation. But that is not sufficient. We have to form really some very, very specific basis sets for these invariant subspaces. And in order to be able to form those special basis sets, we are going to be using the concept of a chain. So I'm going to be drawing this over and over. This is null space of sigma I. And I have null space of sigma I square. Null space of sigma I to the power mi minus 1. And this is the largest null space of sigma I. Okay? So remember, the concept of the chain of vectors starts with a vector x, which is in this disk. This disk is not a subspace, but these ellipsoids are actually subspaces. Each of them are these growing subspaces, and so this is null space of sigma I to the power mi. Sorry. So we would like to here find a basis set for this largest null space. Okay? Because we are trying to find these basis sets for these invariant subspaces, and these largest null spaces are going to be the spaces for which we are going to find the basis sets. Okay? And I know that the dimension of the largest null space is Ri. I currently don't know, because this is a general case, I currently don't know what the dimensions of the smaller spaces. But the eigenspace is the innermost space, and that is where these eigenvectors are living. So in order to be able to form a chain of vectors, we choose a vector x inside the largest null space, sigma I to the power mi, but x should not be inside null space of sigma I mi minus 1. So x should be therefore in this disk, not inside the inner null space here. So what do these two equations mean? It means that sigma I to the mi x is equal to 0, and sigma I to the mi minus 1 x is not equal to 0. Okay? We need to find an x such that it satisfies these two conditions. Can we always find such an x? Yes, because there is a strict growth here from this null space to this null space. And therefore, there should be some extra vectors here which are in this largest null space, but not in the inner null space. Okay? So we find such an x, then we define our chain of vectors, sigma I to the mi minus 1x, as this vector, which is non-zero, sigma I to the mi minus 2x, going until sigma ix and x here. This is our chain of vectors that we have defined in the last lecture and examined in the last lecture. So we know that each of these vectors should be non-zero, because this vector is non-zero actually. Therefore, all of the other ones with lower powers of sigma I should be non-zero. And as a result, we have a set of non-zero vectors, and furthermore, we have proven that, or I showed you how to prove that these vectors are also linearly independent. Okay? How many vectors are there? We know that there are mi vectors here. All right? And then we looked at where these vectors are living in the structure of null spaces. X is living here, and we have shown last time that the first vector is always an eigenvector. Okay? So this is an eigenvector. And the other vectors, generalized eigenvectors. They are not eigenvectors, but they are called generalized eigenvectors. So I know that sigma ix lives here, and then I would have this one as sigma I to the mi minus 2x, and here is where our eigenvector lives in the chain, sigma I to the mi minus 1x. All right? So we are going to form our basis vectors for these invariant null spaces by using this type of chains. I know that the dimension of the null space that I would like to find the basis for is Ri. So if Mi is equal to Ri, since I have Mi linearly independent vectors here, a single chain would be sufficient for finding the basis set of this largest null space. But if Ri is strictly larger than Mi, then I'm going to see that I will need more than one chain of vectors to find the overall basis set for this null space. Okay? And we are going to see that the number of chains that I would like to use is going to have a meaning, and the size of the chains that I need to use for finding a basis set, for the overall basis set for this largest null space, will have a specific meaning. Okay? But currently, without knowing Mi and Ri, we won't know how many chains I'm going to need to find and what should be their sizes. But if Ri is equal to Mi, I know that this is going to be my basis set. And we will see that this chain of basis vectors will put the matrix into its Jordan canonical form. But first here I would like to solve an example, okay, to illustrating this concept of the chain of vectors. So the example is going to be a very simple one, but still I will be able to illustrate the concepts that we have seen so far. 1, 1, minus 1, minus 1, 3, 2, and I have 0, 0, 1. Okay? So this is my example, and what we would like to do is find the characteristic polynomial, find the minimal polynomial, and find the Jordan canonical form, and find the P matrix that would put this matrix into its Jordan canonical form. Okay? So let me first calculate the matrix Si minus A in order to be able to calculate the characteristic polynomial. This is going to be S minus 1, S minus 3, and S minus 1, minus 1, 1, minus 2, 1, 0, 0. Okay? And then I will have to calculate the determinant of this matrix to find the characteristic polynomial. D of S is that I will choose the column or row which has as many zeros as possible, and you see that it's the last row here. So I have plus minus plus here, and S minus 1 times the determinant of the remaining matrix here. So it is S minus 1 times S minus 3, and I have plus 1. Okay? So that is going to be my characteristic polynomial. If I calculate, if I expand these factors here, I will have S squared, and I would have minus 4S plus 4 times S minus 1. Okay? And we see that this is nothing but S minus 2 squared and S minus 1. So this is my characteristic polynomial here, and I would like to find the minimal polynomial. When we have a characteristic polynomial like this, we know that for the minimal polynomial I would have only two possibilities. Either I have the minimal polynomial S minus 2, S minus 1, or I have the minimal polynomial S minus 2 squared, S minus 1. Okay? Minimal polynomial will be either of these ones, and we are going to determine which one it is by looking at the null space dimensions for this matrix. Okay? Sorry. So here I can actually define these sigma matrices. I know the eigenvalues are lambda 1 equals to 2 and lambda 2 equals to 1. And then I can define my sigma 1 matrix as A minus lambda 1 identity. So sigma 1 is this matrix, and sigma 2 is A minus identity. Okay? So now let us look at these matrices. Sigma 1 is A minus 2 identity, I will subtract 2 from the diagonals of this matrix, and the remaining parts will be the same. So I have minus 1, 1, and minus 1 here on the diagonal, and the rest is the same, 1, minus 1, 2, minus 1, 0, 0. So this is my sigma 1 matrix. Let us look at its null space dimension. For the null space dimension, I'm going to look at the rank of this matrix, and then we'll use the rank nullity theorem. How many linearly independent columns does this matrix have? You see that the first 2 columns are linearly dependent, and the last 2 columns are linearly independent. So I have 2 linearly independent columns, meaning that the rank of this matrix is 2. Therefore, the null space dimension, the nullity, should be 1. Dimension of null space of sigma 1 should be just 1. Okay? And did we reach the largest possible dimension at this null space? What is the largest possible dimension? It is the characteristic polynomial power for this eigenvalue 2. I see that I didn't reach, at the power 1, I didn't reach the dimension 2. As a result, the minimal polynomial of this matrix cannot be this one. Okay? Because we need to reach the largest possible dimension 2 at the minimal polynomial power. And here that power is 1, and I didn't reach the characteristic polynomial power as a dimension here. So a minimal polynomial of this matrix cannot be this one, but it is going to be the other one. Okay? So this is my minimal polynomial. And now let us look at if this is making sense. If I calculate sigma 1 square here, its null space dimension has to be 2, which is the second, at the second power, I reach the largest dimension. Okay? So if I take the square of this matrix, you would get these zeros, and I would have here 1, 3, and 1, 4, and I would have 1, and then 2, 3, and then minus 2, 1, and I would have 1. Okay? So this is sigma 1 square, and as soon as I look at that matrix, I see that it has only one linearly independent column. That means that its rank is 1, rank decreased, and the nullity increased. Okay? So I have dimension of null space of sigma 1 square is 2. We reach the highest possible dimension, which is R1, which is 2 here, and we reach that at the power 2, meaning that the minimal polynomial power for this eigenvalue will be 2, and that is going to finalize this minimal polynomial issue. And finally, I'm looking at the matrix sigma 2. Sigma 2 is going to be A minus identity. I will subtract identity matrix from this matrix, meaning that from the diagonals I will subtract 1. Okay? Well, that is going to give me 0, 2, 0, and the rest should be the same. 1, minus 1, 2, minus 1, 0, 0. Okay? So now how many linearly independent columns does this matrix have? I see that these 2 columns are linearly independent, therefore the third one cannot be linearly independent with these ones. So that means that the rank is 2, and dimension of null space of sigma 2 is 1. Did we reach the largest dimension at the first power? The largest possible dimension for this eigenvalue is 1, the characteristic polynomial power. And we reached the R1, which is 1, largest possible dimension at the power 1. That means that in the minimal polynomial, we are going to have the power 1 here, but we already know that by the minimal polynomial properties. Okay? So now let us look at the Jordan canonical form for this matrix. So I have null space of sigma 1. This grows at null space of sigma 1 square. And this is the largest possible dimension, but null space of sigma 1 cube is going to have the equal dimension. So these last two null spaces will be equal. So the dimension of this one is 1, dimension of this one is 2, and dimension of this one is 2. Okay? How many Jordan blocks? So let me write here. Number of Jordan blocks is going to be equal to 1, this dimension, and number of Jordan blocks with size larger than or equal to 2 will be this difference. It is 1. And what about the number of Jordan blocks with size larger than or equal to 3? It is this difference. Then it's going to be equal to 0. So I know that there is no, so these are for the eigenvalue lambda 1. Okay, maybe I should write those. For lambda 1 is 1. For lambda 1, I would have here, this is 1. And for lambda 1, this is 0. So for lambda 1, there are no blocks, Jordan blocks, with size 3 or larger. Okay? And how many blocks whose size is equal to 2? I see that there should be only one block with size equal to 2. And how many blocks with size equal to 1? There shouldn't be any block with size equal to 1. It's going to be this difference. All right? So there is only one Jordan block. One Jordan block with size equal to 2. Okay? For lambda 1. This is for the first eigenvalue. Okay? What about the second eigenvalue? Second eigenvalue is related to this, the blocks of this, the blocks corresponding to the second eigenvalue, and we need to look at the structure of this null space. This null space is a singleton null space like this. Okay? So there is no larger null spaces here. Okay? So I have null space of sigma 2, and there is no larger null space here. Okay? So for the second eigenvalue, I have null space of sigma 1 equals to, null space of sigma 2 equals to null space of sigma 2 square. Okay? And the dimension of this one is 1, and this one is 1. Because this is the largest null space, which is reached at the power 1. Okay? So I see that in this case, what is the total number of Jordan blocks? It is going to be, so number of Jordan blocks with size, in this case, all sizes, number of Jordan blocks with size larger than or equal to 1 for lambda 2. In this case, it is 1. And what is the number of Jordan blocks with size larger than or equal to 2 for lambda 2? And in this case, this is going to be this difference, but this difference is 0. Okay? So 0 blocks for the eigenvalue 2, which have size 2 or larger. That means that all of the blocks for this eigenvalue should have size 1. And there is only one Jordan block, and its size should be 1. So one Jordan block with size equal to 1 for lambda 2. Okay? And this is our second eigenvalue. Okay? So now let me start with the Jordan canonical form. J is going to be one Jordan block with size 2 for the eigenvalue 1. So I have 2, 2. This is my first eigenvalue, and one Jordan block with size 2 here, and one Jordan block with size 1 for the eigenvalue 2, which is 1. Okay, and I would have this one here. So this is my Jordan canonical form for this matrix. Okay. So now I'm wondering what P matrix would bring this matrix A into this Jordan canonical form. Okay, so we have already found the Jordan canonical form of this matrix, and I'm wondering about the P matrix. But before that, let us look at this. M1 was 2, and the size of the largest Jordan block for the eigenvalue 2 here was 2 by 2. So for the first eigenvalue, the largest size of the largest Jordan block is 2, and that is the minimal polynomial power. Similarly, for the second eigenvalue, the size of the largest Jordan block is 1. There is only one Jordan block, therefore the size of the largest one is going to be 1, and this power is 1 here. So you see that when the Jordan blocks have size 1 by 1, the matrix really looks to be diagonal. Okay? So what would have happened if this minimal polynomial power was also 1? Instead of 2, if I had 1 in that case, what would be the Jordan canonical form that I would obtain for such a matrix? If this minimal polynomial was the other one, then the Jordan canonical form would look like this. 2, 2, 1. So I would have 2 Jordan blocks here with size 1, because the size of the largest Jordan block in this case would be just 1. That means that I would have 2 Jordan blocks with size 1, and the other Jordan block would be the same as 1. Okay? In this case, I see that the Jordan canonical form turns out to be a diagonal matrix when all the minimal polynomial powers are 1. Okay? In this case, the Jordan canonical form was not a diagonal matrix because of this 1, which is caused by this minimal polynomial power, which is higher than 1. Okay? So here I get a very, very important fact. If all of the minimal polynomial powers are equal to 1, then the Jordan canonical form turns out to be, it should turn out to be a diagonal matrix. But that also tells us that our matrix A is diagonalizable. So we have actually this fact: a matrix A is diagonalizable. If and only if mi is equal to 1 for all I. If all powers of the minimal polynomial are equal to 1, then the Jordan canonical form turns out to be a diagonal matrix. That means that the matrix A is diagonalizable. Okay? In this case, the matrix A is not diagonalizable, and the Jordan canonical form is not diagonal because the minimal polynomial powers are not equal to 1. Okay? So this is not the Jordan canonical form for this matrix. Okay? For that to be the Jordan canonical form of this matrix, I need to have the minimal polynomial given by this, with all powers equal to 1. Remember, in the earlier lectures, I have also talked about the diagonalizability, and I have told you that a matrix is diagonalizable if and only if it has n linearly independent eigenvectors. This is the same condition. We are going to see this. So a matrix A is diagonalizable, meaning that Jordan canonical form is diagonal, if and only if it has n linearly independent eigenvectors. Okay? So for diagonalizability, these are two equivalent conditions. We are going to see that actually these two conditions are equivalent. If all the minimal polynomial powers are 1, then we are going to have n linearly independent eigenvectors, and if there are n linearly independent eigenvectors, we will have all the minimal polynomial powers equal to 1. Okay? So these are some equivalent conditions. So now I'm wondering what the P matrix is. So I want the Jordan canonical form as P inverse AP, and I want to find what P is. And in order to be able to find such a P, I'm going to be working with these null spaces for each of the eigenvalues. Let us now look at the first eigenvalue, lambda 1. In this case, I have two null spaces. Okay? Null space of sigma 1 is this one, and null space of sigma 1 square. Okay? And the dimension of this one is 1, and the dimension of the largest one is 2. And in order to be able to find the P matrix, I need to find a chain of vectors which would give me the basis vector for this largest null space. All right? Maybe I should erase some parts here. So now let me find my chain of vectors. I know that the chain of vectors starts from the outermost disk. I need to find an x here. X is in null space of sigma 1 square. It should be in the largest null space, but it shouldn't be one inner space. X should not be in the null space of sigma 1. If X is not in this null space, then X shouldn't be an eigenvector, because this is where eigenvectors live. And I want a non-eigenvector which is inside this largest null space. So I'm looking for a generalized eigenvector here. So I'm looking for a vector X which is going to be inside the null space of sigma 1 square. So sigma 1 square X should be 0 and sigma 1 X should be non-zero, because I don't want it to be an eigenvector. Okay? So now what is such a vector? This is sigma 1 matrix and this is sigma 1 square matrix. I am looking for an X vector which, when I multiply that X vector with this matrix, it should give me 0. But when I multiply it with this matrix, on the other hand, it should give me a non-zero vector. Okay? That is what that statement means. If I multiply X with sigma 1 square, then it should give me 0. And when I multiply the same X with sigma 1, it should give me a non-zero vector. Okay? So you see here that if I choose the vector 1, 0, 0, then it would give me 0 when I multiply it with sigma 1 square. On the other hand, if I multiply it with sigma 1, 1, 0, 0 would give me the first column which is non-zero. Okay? So that vector satisfies my conditions. Choose X as 1, 0, 0. Here the selection of X is not unique. There are actually infinitely many different P matrices which would put a matrix into this Jordan canonical form. So this P you find is not really unique. There are infinitely many such matrices. Alright? Actually here, when I find a single P, if I find a single P, I can use P1 equals to alpha P, which is a non-zero multiple of P. Then it would satisfy the same equation. J is equal to P1 inverse A P1. Then P1 inverse is 1 over alpha P inverse. And then A times P1 alpha P. So alphas are cancelling. Alpha should be non-zero. So I get P inverse AP. Okay? So even when you find a single non-zero P vector by P matrix, by scaling it with a non-zero factor, you get another P matrix. So this actually proves that there are infinitely many P matrices that I can find. So here I'm just looking only one of them. Okay? So here, therefore, I can choose other X vectors as well. For example, the X vector 0, 1, 0. 0, 1, 0. It would give 0 when I multiply it with this matrix. And 0, 1, 0, if I take the second column, it would give me 1, 1, 0, a non-zero vector. So the vector 0, 1, 0 would also be possible for my vector in this outermost test. But here I choose the first one that came to my mind, okay, which was 1, 0, 0. All right? So now I'm going to calculate sigma 1x, which is going to form my second vector, the first vector in the chain. Sigma 1x is multiply this vector with sigma 1. It is going to be -1, -1, 0. Okay? So now my chain, this sigma 1x is going to be here. Okay? So you see that sigma 1x should live inside the eigenspace. So this vector should be an eigenvector actually. Okay? So what is multiply -1, -1x, the vector -1, -1x with the matrix A. What do you get? So multiplying a matrix like this with -1, -1x means that sum the first two columns and then multiply the result with -1. Okay? So sum the first two columns, 2, 2, 0, multiplied with -1. The result is -2, -2, 0. Okay? But it is twice this vector, twice the same vector here. That means that this vector is an eigenvector corresponding to the eigenvalue 2. All right? And now let us form our chain. So I have sigma 1x. I start from the eigenvector and write the rest. So this is my first chain of vectors for the eigenvalue 2. Okay? I know that these two vectors are both non-zero and they are furthermore linearly independent. And do you think these two vectors would form a basis for this largest null space? The largest null space has the dimension 2, and I have found two linearly independent vectors in that null space. Okay? Therefore, this single chain is going to form a basis for this largest null space. All right? So I'm going to stop here. So I found all of my basis vectors necessary for the first eigenvalue, because this dimension of this null space is 2, and I have already found two vectors by using a single chain of size 2. Okay? So this is the computations for the first eigenvalue. And now let me go into the second eigenvalue. In the second eigenvalue, I have only a single null space of sigma 2. Okay? And the dimension of it is 1. All right? And now I'm wondering about what to choose, how to choose the chain of vectors. So how do we choose the chain of vectors? X should be inside the outermost, so here I will call the vector y. Y should be inside the outermost null space, sigma 2 to the 1. In this case, I have 1 as the highest power. And y should not be in the inner null space. But there is no inner null space here, okay? But what is going to be that inner null space? Inner null space is going to be null space of sigma 2 to the 0. Okay? But what is null space of sigma 2 to the 0? This is going to be null space of sigma 2 to the power 0 is the identity matrix. And what is the null space of the identity matrix? Which x vectors gives 0 when I multiply it with the identity matrix? It is only the 0 vector that will satisfy that null space condition. So null space of identity matrix is composed of only the 0 vector. And I want my y in this largest null space, but my y should not be in the inner null space, which is composed of only the 0 vector. Okay? So what do these two conditions tell you? If y is not going to be inside the 0 subspace, y should be non-zero. Okay? So the second condition is that we need to find y inside null space of sigma 2, and y should be non-zero. Okay? It is coming from the second condition. So a non-zero vector inside this null space. This is my eigenspace. A non-zero vector inside the eigenspace is an eigenvector. Okay? So in this case, I only need to find a single non-zero vector. I only need to find a single eigenvector in order to be able to find the chain of this eigenvalue. Okay? So I need to find a non-zero vector inside the null space of sigma 2. Okay? Give me one non-zero vector inside the null space of this matrix here. So you can think about it, but it is going to be the following vector. So y is going to be just 4, 1, 1. Okay? If you multiply this y vector by that matrix, you're going to get 0, and this is a non-zero vector, trivially. Okay? So my chain here is going to be composed of only a single vector. Okay? Because there is only a single null space here. There are no concentric null spaces which would make the size of the chain larger than 1. Okay? So the size of the chain here is going to be 1, and I would only have a single vector. So this is my chain 1 and for lambda 1, and this is my chain 1 for lambda 2. And do you think this single y, this single chain forms a basis for this largest null space? Yes, its dimension is 1, and I found only a single non-zero vector inside that null space, and that means that I have actually found my basis set with a single chain. Why are these happening? We are here stopping by finding only a single change because the minimal polynomial powers are equal to the characteristic polynomial powers for these examples. Ri is equal to mi for all I for this example. That is why we stop by finding only a single chain. Okay? A single chain always forms a basis when Ri is dimension of the space is equal to the mi, which is the chain size here. Okay? So we have found our chains here. And do you think this is an eigenvector? This y, 4, 1, 1. It has to be an eigenvector, right? If you don't believe me, just multiply this matrix with this vector, 4, 1, 1. Then you are going to get, again, 4, 1, 1. Okay? 4 times 1 plus 1 times 1, 5 minus 1 times 1. So I have minus 1, which is 4. And if I sum these, 5 minus 4 times this, 1. And I would have 1. So when you multiply A with this vector, you would get again 4, 1, 1, which is 1 times this vector, which means that this is an eigenvector corresponding to the eigenvalue 1. All right? So now I have found all of my chains here. Okay? And each of my chains form a basis for the largest null spaces. And now I'm wondering whether if I form my P matrix out of these chains, then I'm going to obtain the Jordan canonical form when I change the basis. Okay? So let me form my P matrix like this. P is equal to sigma 1 x. I put the first chain there. Sigma 1 x x. And finally, I put y here. This is my P1 matrix, and this is the P2 matrix. Okay? So my P matrix is going to be then sigma 1x is minus 1, minus 1, 0, and x is 1, 0, 0, and finally y is 4, 1, 1. Okay? This is my P matrix. And now I'm wondering if I change my basis with this basis change matrix, I would obtain the Jordan canonical form as the new A bar matrix. So I'm wondering about what A bar is if I multiply P inverse with A and then with P. Okay? So we know that I use this equation always in the following form. P times A bar is equal to A times P. In this case, I won't need any inverses. Okay? Let me write P here. Minus 1, minus 1, 0, 1, 0, 0, 4, 1, 1, times I would have the A bar. I currently don't know what A bar is, and my wish is A bar to be equal to the Jordan canonical form. Okay? Is equal to A times P. A is this matrix, 1, minus 1, 0, 1, 3, 0, minus 1, 2, 1. Okay? Times P itself, minus 1, minus 1, 0, 1, 0, 0, 4, 1, 1. Okay? So you see that I know everything on the right, so I can do the multiplication on the right. So I would have minus 1 here. It's going to be sum these two columns and multiply it with minus 1. So I have minus 2, 0. I know that the first vector was an eigenvector, so this is my result. And 1, 0, 0 is going to give me the first column. And 4, 1, 1, if you multiply 4, 1, 1 with A, you would get 4, 1, 1. Just check this. Okay? Now, in order to be able to find the columns of A bar, I will express the columns on the right-hand side as a linear combination of these columns here. Okay? So express minus 2, 0 as a linear combination of the columns here. Okay? It is going to be minus 2 times the first column, plus 0 times the second column, plus 0 times the third column. So minus 2, 0 is 2 times the first column, plus 0 times the second column, plus 0 times the third column. Okay? So I would put here 2, 0, 0. Okay? Which are these coefficients. And now express 1, minus 1, 0 as a linear combination of these two columns. I know that minus 1, 0 is already in this null space, which is invariant. As a result, I need to be able to express minus 1, 0 as a linear combination of only the first two columns. And the third coefficient will be automatically 0 because these null spaces are invariant, remember? And minus 1, 0 is inside this largest null space, which is invariant. As a result, when I multiply 1, 0, 0 here, when I have this minus 1, 0, sorry, when I actually try to write this 1, minus 1, 0 as a linear combination of the columns here, it is going to turn out to be the linear combination of only the first two columns, and the third coefficient will be equal to 0. Why was that? Because this 1, 0, 0 here is already inside this largest null space, and minus 1, 0 vector is nothing but A times 1, 0, 0. If this null space is invariant under A, and x is inside this null space, then when I multiply x with A, then I would get another vector inside this null space. That means that this 1, minus 1, 0 vector should also be inside this null space, because this null space is invariant. Why? Because this null space is nothing but a null space of a polynomial of A. Okay? So I need to be able to express 1, minus 1, 0 as a linear combination of these columns. I see these first two columns. So I see that here, in order to satisfy, so what are the coefficients? So I would put 1 here, and I would put 2 here, and I would put 0. Okay? So 1 times this column plus 2 times the second column plus 0 times the third column would give me 1, minus 1, 0. Okay? So now let me write this coefficient 1, 2, and 0. Okay? And finally express 4, 1, 1 as a linear combination of these columns. This is really trivial. It is going to be 0, 0, 1. So you see here that this A bar is really actually our Jordan canonical form. Okay? Which is this thing. Okay. So you see I have a 2 by 2 block and 1 by 1 block here for the eigenvalues. And why did this happen? Because we have selected our basis vectors for these null spaces to be in a very specific form, and they were composed of chains of vectors which we carefully selected. And here I'm going to tell you something that we are going to see more about. So here for the eigenvalue 2, I had a single Jordan block with size 2. For the eigenvalue 2 in the Jordan canonical form, I had a single Jordan block with size 2. And look at the chain for the first eigenvalue. I have a single chain with size 2. Okay? For the second eigenvalue, I have a single Jordan block with size 1. And look at the chain for the second eigenvalue. Single chain with size 1. This is always going to happen when we try to find the P matrix. The number of Jordan blocks will be equal to the number of chains that you're going to find, that you need to find for those eigenvalues. And the size of the chains will always be equal to the size of the Jordan blocks corresponding to that eigenvalue. Okay? So here, before I finish, I'm just going to be looking at what happens when I change my P matrix a little bit. Okay? So the thing that I'm going to do is the following. So suppose that I change my P matrix a little bit. Instead of putting this chain there, suppose that I have mistaken the order of the vectors inside the chain. So suppose that therefore I choose my P matrix as follows: X, sigma 1 X, and Y. Okay? In this case, what would be my A bar matrix? Let us look at that equation. So P in this case would be X is here 1, 0, 0, and -1, -1, 0, and Y is 4, 1, 1. Okay? So when I reorder my vectors inside the P matrix, in that case, what is going to happen to A bar? So let me write P here. Times A bar. So that is my A bar. And here A times P. A is this matrix. Times P, 1, 0, 0, -1, -1, 0, 4, 1, 1. And in this case, if I do this multiplication, you would see that this is going to be 1, -1, 0. And I would have this -2, -2, 0. And 4, 1, 1 is going to be 4, 1, 1 again. Okay? So now, in order to be able to find this new A bar, I need to express these vectors, these columns, again in terms of the columns of P here. That is my P, and that is my P. Okay? So now let us first do the second column. Second column is nothing but twice the second column here. So the coefficients for the second column will be 0, 2, 0. Okay? So you see that this 1 is no longer there. This 1 is no longer there. Instead, I would have 0 here. So 1, -1, 0. This is going to be 1 times this second column plus 2 times this one, and I have this. So I would have 2, 1, 0 here, and 4, 1, 1 it will be 0, 0, 1. So you see that I get another A bar, but is this in Jordan canonical form? For our purposes in this course, this is not in Jordan canonical form, but I want to tell you that for some books on linear algebra and for some instructors, even in this department actually, the Jordan canonical form, ones of the Jordan canonical form are below the main diagonal. Okay? So they are, when in some books you would see Jordan canonical form in this form, where these ones are below the main diagonal instead of above the main diagonal. Okay? And this happens with a reordering of the chains of vectors. If you reverse the chain of vectors inside the P matrix, then these ones turn out to be below the main diagonal. Okay? So according to the general literature, so this matrix is also in Jordan canonical form. Okay? There are some people who define the Jordan canonical form just in this form. Okay? But in our course, we will always order our chains with the eigenvalue coming first. So sorry, the eigenvector coming first. Okay? So we will always order our chains from the inside towards the outside. Okay? The other order is from the outside to the inside, and they would result that order would result in a Jordan canonical form where ones are below the main diagonal. Okay? So you can just know that when we change the order of the vectors inside the P matrix, you can get different type of Jordan canonical forms like this. Okay? But for the purposes of this course, we are not going to consider this as in Jordan canonical form. Okay? So I can also look at other possibilities. For example, what happens when I take my P to be this? I can put Y first, okay? And then I can put my other sigma 1 X and X, the other chain. If you calculate the A bar coming with this P ordering, you would get 1 here and 2, 2, 1. Okay? So if you put the chain of the second eigenvalue first, then you would get in the Jordan canonical form that eigenvalue first, and then I would have the first eigenvalue with the second chain. Okay? So this matrix is also in Jordan canonical form for our purposes, but as I told you in this course, we will always try to order the Jordan blocks from the largest to the smallest. Okay? Largest at the top and the smallest at the bottom. Okay? But this is of course also in the Jordan canonical form. So by changing this P matrix structure, the order of the vectors, you can get other simplified matrices, and you can change the order of the blocks in the Jordan canonical form, or even you can change the form of the blocks by changing the order of the vectors inside your chains. Okay? So this completes this example, and now we're going to finish this lecture by considering two special cases. Special cases. In this case, we have two special cases, and case one is going to be, let A have a single eigenvalue, lambda I, and mi equals to Ri. Okay? So this is going to be one of the extreme cases that we can encounter. And I have already talked about what happens when mi is equal to Ri. Okay? And in this case, let us see what is going to happen. So I have only a single eigenvalue. Let us say that A is in Cn by n. And I know that Cn can be decomposed as, let me define sigma I here. A minus lambda I identity, and I know that Cn can be decomposed to be null space of sigma I to the mi. Okay? And I know that the dimension, this happens because of the fact that I can decompose Cn always into these null spaces. Okay? And I see that the dimension of this null space should be Ri. All right? But here, I see that the dimension here should be the dimension of the overall space. That means that I get the equality here. Ri should be the dimension of Cn, which is n. So in this case, Ri should be n and mi should be n. They should be equal to the size of the matrix. Okay? I can actually write here also mi. In this case, I have this important fact. I have only a single eigenvalue, and this minimal polynomial power is equal to the characteristic polynomial power, and they should all be equal to the size of the matrix. Okay? So d of s is s minus lambda I Ri, which is equal to mi, which is equal to n, and m of s is equal to d of s, the characteristic polynomial. Okay? So I would have s minus lambda I, Ri equal to mi equal to n. Okay? Now let me look at these null spaces here. So let me write them here. Null space of sigma I, null space of sigma I square. These continue until null space of sigma I mi minus 1, and null space of sigma I to the power mi. I know that the dimension of this thing is Ri. Okay? So the dimension of this thing is Ri, but I know that Ri is equal to mi in this case. Okay? I know that all of the other null spaces should have strictly smaller dimensions. Okay? Dimensions should strictly decrease towards the left. And I know that the dimension of the null space of sigma I should be larger than or equal to 1. All right? So now how many spaces do I have? 1, 2, going until mi. I have mi spaces. And their dimensions should strictly increase until we reach the number mi. Okay? I have mi spaces, mi distinct spaces which are inside each other, mi concentric spaces like this, and the dimensions of the largest one, is mi. And the dimensions of the others should strictly increase. They cannot remain equal. Okay? Mi spaces with distinct dimensions, with strictly increasing dimensions, and the dimension of the largest one should be mi. Now what can you say about these dimensions? For example, can the dimension of null space of sigma I be equal to 2? If I start at 2 and suppose that the increase is just equal to 1, 2, 3, 4, and at the end you're going to reach mi plus 1. Okay? So at the end, the largest dimension that you need to have is going to be mi plus 1. So even this one cannot be equal to 2. So the dimension of this one should be 1 in this case, dimension of this one 2, and this should continually increase. Dimension of this one should be mi minus 1, and the dimension of this one is mi. This is the only possibility in this case. So these null spaces, each one, the dimension of each one should be one larger than the smaller one, than the earlier one. Okay? So otherwise, I cannot satisfy these strict inequalities here. Okay? With this largest one equal to mi. All right? So now I can look at the Jordan canonical form for such a matrix. So number of Jordan blocks for the first eigenvalue. There is only a single eigenvalue in this case. This is going to be 1, this dimension. Okay? Number of Jordan blocks with size larger than or equal to 2 is going to be this difference, which is 1. Larger than or equal to 3 is 1, the other difference. And this is going to continue until this one. Larger than or equal to mi is just going to be this difference, which is equal to 1. Okay? What about this time, the number of Jordan blocks with size mi plus 1? This is going to be this difference, but the null space of sigma I to the mi plus 1 is going to have the same dimension as this one. So this one is going to be 0. So now what can you say about there is only a single Jordan block, and because of this number, and what is its size? There is only a single Jordan block, and what is its size in this case? I know that if this number is 0 and if this number is 1, then I know that there should be one Jordan block with size equal to mi. Okay? So in this case, one Jordan block with size equal to mi for lambda I. Okay? There is only a single Jordan block in this case. And this is what happened in our earlier example. In our earlier example, our i's were equal to mi, okay, in the 3 by 3 example. And for each eigenvalue, we had only a single Jordan block, okay? And this is always happens when we have the minimal polynomial power of an eigenvalue is equal to the characteristic polynomial power of the same eigenvalue, okay? One Jordan block with size mi, but I know that mi is equal to ri, and that is equal to n. Okay? So the Jordan canonical form of this matrix is going to be a single Jordan block with size n by n, which is formed of the eigenvalues on the main diagonal, and once below the main diagonal, once above the main diagonal, and I would have zeros everywhere else. Okay? So now what about the P matrix? I know that I can, now we're asking the same question over and over. So I want to find a P matrix that would satisfy this equation. And what is the P matrix? In this case, we know that just as in the earlier example, only a single P matrix would suffice. Okay? So I would only find only a single chain, and only a single chain will suffice in this case. Okay? Will be sufficient. Okay? Let us choose our x. X is in null space of sigma I to the power mi, and x is not in null space of sigma I to the mi minus 1. Okay? If I choose such an x, then I would have sigma I mi minus 1x, sigma I mi minus 2x, going until sigma I x and x. A single chain of vectors given here. Okay? And there will be mi vectors here. Mi vectors, or ri vectors, or n vectors. Okay? So there are already n vectors here, which are in this largest null space. So since Ri is equal to Mi, with a single chain, I will be able to form a basis for Cn, or for the overall null space here. Okay? So I'm going to form my P matrix out of these chain vectors. Sigma I Mi minus 1x, Mi minus 2x. This is going to be an n by n matrix. Okay? Sigma ix and x. This is my P matrix. And now I'm going to, so this matrix is going to be invertible because all of its columns should be linearly independent. So we could fill our P matrix with only a single chain. Now I'm going to wonder about the following. So I have what is A bar is equal to P inverse AP. All right? I'm wondering A bar, which is P inverse AP. So now let me write the equation in the form that I'm going to use it. P times A bar is A times P. Okay? So let me write P here. Sigma I Mi minus 1x, sigma I Mi minus 2x, going until sigma ix and x. This is my P. A bar, I will fill it in. And let us put here A times P. A times P again. Sigma ix and x. Okay? Now we can always make the multiplication on the right here. This is going to be A times sigma I Mi minus 1x, sigma I Mi minus 1x, A times sigma I Mi minus 2x, A times the columns of this matrix. Okay? So we have here A times sigma ix and A times x. All right? So now what do I have to do? I have to express these columns here in terms of the columns of this P matrix here. Okay? And then I will write the coefficients as the columns of A bar. Okay? I need to express the columns here as a linear combination of the columns of P again. And the coefficients would form the columns of A bar. All right? A times sigma I Mi minus 1x. What is this? I know that the first element of all chains are eigenvectors. So this is actually an eigenvector. How can I see that? So sigma I times sigma I to the mi minus 1x should be equal to 0. Why is that? Because x is inside sigma I, null space of sigma I to the mi. And when you do this multiplication, you would get sigma I to the mi times x. The result should be equal to 0. As a result, sigma I mi minus 1x is inside null space of sigma I, in the eigenspace. Or you can do the following. Instead of the sigma I can write a minus lambda I identity times sigma I mi minus 1x. Should be equal to 0. Okay? And that gives me a times this vector, a times sigma I mi minus 1x, minus this lambda I identity times this vector. This is lambda I times this vector. Should be equal to 0. But this tells me that a times this vector is nothing but lambda I times the same vector. Okay? A times sigma I mi minus 1x is lambda I sigma I minus 1x. Okay? That tells me that this sigma I mi minus 1x is an eigenvector. Okay? For the eigenvalue lambda I. So what can you say about a times this vector in terms of these vectors, these column vectors? Okay? Tell me the coefficients of this multiplication in terms of these vectors here. You know that the coefficients would be lambda I, 0, 0, 0, all zeros until the end. So what about the first column? A times this is lambda I times the first vector here. This means that the coefficients would be lambda I, 0, and all zeros until the end. Okay? This is the first column of A bar. What about the second column? Now I need to express A times the second vector of the chain as a linear combination of these columns. And the coefficients should be put here into the second column. Okay? So this vector, when expressed in terms of these columns here, the coefficients would form the A bar second column. Okay? Now let me take this vector. In order to be able to find this, I will use a similar idea. So let me take this second vector, sigma I to the mi minus 2, mi minus 2x. I have this vector. What happens when I multiply it with sigma I? Just like here. I know that I would get the first vector here. Okay? So this is going to be sigma I mi minus 1x. So you see that when I multiply the second vector here with sigma I would get the first vector. Okay? Now instead of sigma I would write A minus lambda I identity times this vector is going to be the first vector. Okay? Now let us distribute this multiplication. A times the second vector, sigma I mi minus 2x, minus lambda I times identity times this vector will be itself, mi minus 2x, is going to be the first vector, lambda I mi minus 1x. Okay? Now take this lambda I multiplicative term to the right. Okay? A times sigma I mi minus 2x is, I would have the first term, first vector in the chain, plus lambda I, sigma I to the mi minus 2x. Okay? So now you see that this second column, A times the second vector in the chain, can be written as 1 times the first column of P plus lambda I times the second column of P. Okay? 1 times the first column of P and lambda I times the second column of P, and I would have 0 coefficients everywhere else. Okay? And the interesting thing here is that you can apply this logic to any column here. when you multiply any column here with sigma I, you get the earlier vector here. Okay, you get the previous vector in the chain. All right, and then you would always satisfy this type of equation. Sigma I times a column would give the previous vector. Okay, and then expand sigma I there, and you would always get A times a column here is the previous vector plus lambda I times the same column. Okay, you can always get that type of relationship. So if you fill the first column, third column here, you would get lambda I times the column itself plus 1 times the previous column and zeros everywhere else. Okay, so you can do this, apply the same logic to everywhere, and if you continue in this manner, you would get the A bar matrix given by this matrix, which is the Jordan canonical form of A, okay, which is given like this. So these chains, their special structure allows us to form a single Jordan block here. Okay, a single chain forms a single Jordan block with the same size as the chain here. Okay, so this is one of the extreme cases when the minimal polynomial power of an eigenvalue is equal to the characteristic polynomial power of an eigenvalue. In that case, I would have a single Jordan block with the size equal to the characteristic polynomial power or minimal polynomial power. Okay, and you see also why the structure of the chains are causing at the end the forms of the matrices to be equal to the Jordan canonical form here. Okay, so because in the chain, when I multiply any element of the chain with sigma I, then I would get the previous element, just like this one. When I multiply the second element of the chain with sigma I would get the first element of the chain. Okay? Then instead of sigma I, if I write A minus lambda I identity, I would always get A times an element of the chain would be equal to the previous element of the chain plus lambda I times the same element of the chain here. That is why these Jordan canonical forms are turning out in this form here. Okay? This is only not happening in the first element here. When I multiply this one with sigma I, the first element with sigma I would get 0. That is why in the first element I don't have this previous element, because in the chain there is no previous element to the first element there. Okay? So this was one of the special cases, and the second special case here will be the following. I would get d of s equal to s minus lambda I to the power ri, and m of s is going to be s minus lambda I. So the other extreme of the same picture will be when this minimal polynomial power is equal to 1. Okay? And that is going to give us another simple Jordan canonical form. In this case, I had only a single Jordan block with a large size. In this second special case, we are going to have n Jordan blocks with size 1 by 1. We're actually going to have a diagonal Jordan block, because diagonal Jordan canonical form, because this power is 1 here. Okay, and that is going to be our other extreme. And every other matrix that we are going to consider will fall in between these two extreme cases. Okay, and we are going to see what we can do in such cases as well. All right. But this special case is going to remain for the next lecture. That's all for this lecture. Thank you for watching.